Let me now show that there is a direct link between the accuracy of a medical test and the statistical power of the study that you conduct. Back to the reliability of the cancer test. How much you updated your prior of having cancer of 0.5% greatly depends on the accuracy of the test at the hospital, i.e. the likelihood, the chance of having a positive test result if you indeed have cancer. I showed you how much we updated the prior in case of a likelihood of 99%. So the test is 99% accurate. In that case, you adjust your prior to 0.33. And that means that the adjustment factor, so the change in the probability that you assign to having cancer is actually 66. So because you divide your posterior of 0.33 by your prior of 0.005, and that's 66. We also call this the base factor. That's basically what you learn from your cancer test. If the test is less accurate, say that it has an accuracy of 90%, then even though that may sound good, it means that you learn a lot less from this test, because then your posterior is only 0.04. So if you have a positive test result, then there's a 4% chance of indeed having cancer. Isn't that amazing? That's actually what I show here in the next slide on the cheat sheet. And the trouble here is with the large population of people that do not have cancer, which is great of course, but what happens is that if you have a not so accurate test, then out of those 9,950, we get 10% of them, we have 10% of them getting a positive test result, which is almost 1,000 people. So this goes up by a factor of 10, right, which is huge. So we have a huge number now of people that do not have cancer but get a positive test result. So obviously this test, even though it has an accuracy of 90%, is not going to be very informative. You don't learn much from it, given that cancer, the chance of having cancer is so low, right? So back here, so with a lower likelihood, more people get a positive result even though they do not have cancer, i.e. the signal from this test gets more noisy. It's not only noise, but the signal is not very strong. So an unreliable test lowers strength of evidence. And let's now define strength of evidence. What does it mean? It's by how much your posterior changes relative to your prior. And that's an indicator of how much you learn from a test, what a test contributes. Another name is for it, as I just mentioned, is the base factor. What does it really mean? So a base factor of 66, when we divided the posterior over the prior, what does that mean? The data are 66 times more likely to have occurred under the alternative hypothesis, I have the disease, than under the null hypothesis, I do not have the disease. If the base factor is 0.1, then the data are 10 times more likely to have occurred under the null hypothesis, I do not have the disease, than under the alternative hypothesis, I do have the disease. A rule of thumb for interpreting the base factor is Jeffrey's scale. If your base factor, so posterior over prior, has a value between 1 and 3, then it's barely worth mentioning. That actually holds for the test for anemia, which had an accuracy of 95%. And then I actually updated the probability of having anemia, well, actually an iron deficiency, from 0.3 to 0.9, which sounds great, but it's a base factor of only 3. So I didn't learn too much. I already put my probability pretty high. Now it's higher, but you may wonder whether this test is really worth it. I should really get a test with a higher accuracy. For higher base factors, then the strength of evidence is going to be stronger, so it's substantially strong or even very strong if your base factor is larger than 30, which held for the cancer test. So remember, we only went from 0.5% to 30%, so it sounds like, well, all you know now is that you have 30% of having cancer, but that's, you learn a lot because you started very low. Your prior was really tiny, right? So it's now 66 times larger. So this is obviously very strong evidence. Now we actually go from the medical context to your own empirical work, and then the reliability of the test, i.e. the likelihood, is the statistical power of your study. Remember, power stood for the chance of getting it right. The a priori, so before you conduct your study, probability of identifying effect, which means rejecting the null hypothesis of no effect, if there is an effect. And the lower the power of your study, the lower the likelihood, and the noisier the signal, so the less informative the result. And remember from week 2 in Econometrics 1, for those of you who followed it, then you actually learn to choose a sample size so that you get it right 80% of the time. And I actually put the knowledge clip and the slides related to statistical power from Econometrics 1 on the Canvas course page of Econometrics 2 under module 4. Let me stress one more time that power is something that you have to compute before you conduct your study. It's meaningless once you have conducted your study. It's all about what is the chance of getting it right if I would conduct my study. Let me briefly revisit power. If you want to know more details, then go to the knowledge clip from Econometrics 1. Say that you think that your treatment has an effect of +1, so that is your prior. Then you can actually plot the distribution of estimated coefficients if you run your experiment many times. I actually showed that in Econometrics 1 based on simulation in R. And again, this should not be surprising that if you have a certain design of your study, then you can get a range of coefficients, right? So you're not always getting exactly 1. Obviously, the chance of getting a result of 1 under the assumption that your treatment effect is 1, that probability is the highest, but you still may get 4 or -1. Cannot be excluded, even though the probability is small. Now, when will we be able to provide evidence for an effect of 1? Right, so when are we going to get it right? Well, if we are able to reject the null hypothesis of no effect. When are we able to reject the null hypothesis of no effect? Well, that happens when we are in the tails of the distribution of the red curve, so the distribution of the estimated coefficient under the assumption that the effect is 0. Right? You can also draw this curve under the assumption that there's no effect, and then only if you end up in the tail, so if you get a t statistic of 1.96 or higher, then you reject the null hypothesis of no effect, and then you know your power, right? So what is the probability of detecting an effect if there is an effect? That is when you are in the tails of the red curve. And now, under the assumption that there is an effect, then the whole green area under the curve is your power. And remember, I'm showing you the one-sided test, but we always do two-sided tests. So what do we have? We have alpha, which is usually 0.05, and the probability that the test statistic t-value falls beyond the critical value, assuming that the null hypothesis is true. The power is the probability that the test statistic falls beyond the critical value, assuming that the alternative hypothesis is true. And generally we aim power to be 80%, 0.8, which means that if we repeat the experiment many times, then in 80% of the cases we find a statistically significant effect. Now, you may have noted that 80% sounds good, but if we compare that to a medical test, then we were talking about accuracy rates of like 0.99, right, or maybe 0.95, but not 80, right? So that's very different. So generally our requirements for power are not very high, but as we'll see later, in practice, the statistical power of our studies is way below 80%. Determinants of power. The larger your sample size, the higher your power. It is easier to detect a large effect relative to a small effect, and then if you want to have a high reliability, if you set alpha really low, so the level of statistical significance, then you get a smaller chance of rejecting the null hypothesis of no effect. So the green area is also going to be smaller, so then your power is also lower.